LMS invited lecture series today, and the second lecture will be on probabilistic approach to compressive or compressed sensing, whichever. So thank you, Emmanuel.
Yeah, thank you very much. So we're going to call it CS for short from now on. Okay, so just to see where we are, so we did some introduction and some history yesterday. Today we're going to dive into the heart of the matter. I think the next 3 lectures are going to be fairly conceptual. And then, as I said, towards the end of the week, we'll talk about other kind of topics, matrix completion, large-scale optimization, and application. So for today, this morning, this afternoon, and tomorrow morning, we're going to have more conceptual lectures. Okay. All right, so the theme for this lecture is to study a probabilistic approach to compressed sensing. We're going to look at acquisition by random sensing. We're going to discuss one important notion, which is a notion of incoherence. I'm going to introduce an incoherent sampling theorem, which I hope to give you some ideas of how it's proven tomorrow morning. Then we're going to talk about why is it that L1 works so well. And then I'm going to give you a first easy proof, a proof of recovery by L1 from simple measurements that you can actually almost teach undergraduates. And so we'll see how it goes. Okay, so yesterday we talked about idealized sampling. We know that most of what we sense is structured. Structure for us means sparsity. So we know that we're about to sense the world, but the world is not as complex as it might seem. And so we may be sensing a vector that looks like this, which is kind of sparse, or a vector which is nearly sparse as all the kind of images we discussed yesterday. And of course, if I had an oracle that was telling me exactly which coefficient is not 0 and which coefficient is 0, I could actually point my sensor and measure exactly what I need and not what I don't need, which is what we argued about yesterday. So if we had an oracle, I could, of course, tremendously reduce the number of measurements I need to take, because what I would do is I would just store the information I need and not bother storing the information that contributes nothing or very little, and so I could effectively do simultaneous acquisition and compression. But of course, these positions, where information is going to lie, I have no idea a priori, and so I would not know a priori how to sense or what kind of measurements to take about simple things like this, so that I can recover the locations where things happen and the magnitude of these things. Okay, and so that's what we're going to talk about today. All right, so I would say that when you try to brush a broad theory of compressed sensing, I would say that there are 2 main approaches that emerge. One is a probabilistic theory. That's what we're going to do today, and you'll see that it's extremely simple in its formulation. There's another theory which is more deterministic, which goes through the machinery of restricted isometry. Of course, it uses probability at some point. All the theory of compressed sensing is probabilistic in nature, but the advantage of the second type kind of theory is that it kind of completely disentangles what the probability from the deterministic part. Okay, so today we're really going to study the probabilistic theory, which is very, very simple and is broadly applicable, I believe. And this afternoon we'll study the deterministic approach. Okay, so this first this probabilistic approach is a theory that came about not long ago, about a year ago, and so I think it's in many ways the way I would tell people in the street what compressed sensing is. It's the most simple explanation and the most simple mathematical formulation I could find. And so that's what I want to present today. All right, so we're going to acquire signals by random sensing. We made this point kind of yesterday. All right, so we have this digital signal which lives in Rn. We're going to measure it by making measurements, that is by correlating the signals with waveforms AK, so that we assemble this underdetermined system of equations, B equals AX. And just to remind everyone, we have m rows in X and columns, m rows in A and columns in A, and so our matrix A is, as usual, largely underdetermined. All right, so A looks like this. We have m rows and columns. And so each row of A is a vector AK, and we're going to assume that we're going to choose these sensing vectors IID from a population F. So that's very, very simple model. I have a bag of sensing vectors. Each time I want to make a measurement, I sample a vector from my bag, I calculate inner product, and that's it. You want another one? I sample another one, calculate inner product, and that's it. Okay, so this is really a very simple sensing mechanism. I sample sensing vectors, I observe AK transpose X, and that's my measurement. Now, about this population of sensing vectors, we're going to require two properties. The first is a property we're going to call isotropy, and this says that if I look at the expected value of the rank 1 matrix AA transpose, it is the identity. Okay, so this is a very simple property. What I want is that if you think about your population, it's saying that the covariance matrix is the identity, that somehow the entries are uncorrelated. Okay, so this is the first property, which we're going to discuss in a minute, but what this is saying is that the expected value of AA transpose is the identity. That's property number 1. And property number 2 is what we discussed heavily yesterday, is this incoherence notion. What I'm going to want from these vectors A, I want from this vector A that they are spread. And so I'm going to have a parameter mu, which we're going to call the coherence of the population from now on, or the coherence of your sensing mechanism. And the coherence is a convenient stochastic upper bound on the maximum entry of a vector A. Okay, so what we argued yesterday, we want these vectors A to be fairly flat. All right, so we want this coherence to be fairly low. Okay, and so this inequality just needs to hold in a stochastic sense. That is, with large probability, I want that the maximum of this is less than a quantity mu. Okay, this quantity mu we're going to call the coherence. Okay, and that's the only two assumptions we need in the theory. One, I'm sampling vectors from a population. This population has this property, and the vectors I'm getting are not spiky. Okay. So let's look at the coherence assumption. Of course, the coherence assumption says, in fact, I could relax the condition I want on the expected value of AA transpose. I could just require probably that it's bounded away from 0 and infinity. And so I'm going to just assume that the expected value is the identity for simplicity, but I am sure that there's a theory that would hold for a covariance matrix which is bounded away from 0 and infinity. Okay, and why do we want this? Well, we want this. Suppose the expected value of AA star were rank deficient, like it would not be positive definite. Then what does it mean physically? It means that there are directions of space that you would never see, you would never sense. It would mean that all your vectors, your sensing vectors lie in a low-dimensional plane. There are directions of space that you would never explore, and even if you were taking infinitely many measurements, you would not even be able to tell me what the signal is. Okay, so this coherence assumption, this isotropy assumption is very, very natural. It says that, well, if we did not have something like this, then of course I would not be able to do anything. For example, suppose that all the time I sample a vector, it's always the same. That would be a bit of a problem. Okay? So this is saying that the population is rich enough so that I explore all directions in space. And the second is this incoherence property, which says that these vectors are spread out. Okay, so the coherence, the isotropy condition, I'm not going to discuss anymore. It's really this idea that we want to explore every direction in space and not have sensing measurements that live in a low-dimensional plane. Otherwise, even if you have infinitely many measurements, there's nothing you could do. Okay, so now we're going to look at examples of measurement that fit this model. Okay, and there are many. So I'm going to use temporary notations to think that, let's say we're sensing a 1D signal, in which case our sensing vector A has n components that I denote by A1 through AN. so that the i's component of ai is simply the inner product between A and the i's canonical basis vector. Similarly, for matrices, we can have the same notation where the ijth entry of the matrix is denoted by the usual way. Then, of course, AA star, which is this rank 1 matrix, is of course AI times AJ bar. It's a rank 1 matrix. These entries are the outer products. So it's a value AI AJ complex conjugate. And the requirement that the coherence, that the system is isotropic, means that the expected value of this quantity must be 1 on the diagonal and 0 outside. And so on the diagonal, it means that the expected value of AI squared is 1. And therefore, I know that the coherence needs to be at least 1, because the coherence is the maximum value that these components can take. So because on average, on the diagonal, I see that this quantity is 1, then I know that no matter what I take, the coherence has to be greater than 1. And what we're going to argue is that we're going to want coherence close to 1 for very efficient sensing. Large coherence, bad sampling results. Low coherence, good sampling results. Okay. All right, so the picture is what I've shown you before. The signal is very local, but what you're going to do is you're going to make global measurements, incoherent measurement about this signal using random vectors drawn from a population that is both isotropic and incoherent. Okay. So let me first give you an example of a bad sensing mechanism. A bad sensing mechanism would be a coherent one. And what is the most coherent sensing mechanism I can think is each time that you want to make a measurement, pick a coordinate and measure xj. So mathematically, this would say that I would pick j, a coordinate, uniformly at random between 1 and n. I would set my sensing vector to be square root of n times ej, so that E of A star, A star is the identity. That's just a normalization you need. I would pick A to be square root of n times ej, so that the expected value of A star would be 1 over n times this. It's the identities. That's what we want. We have our isotropic condition. And for this sensing mechanism, of course, the maximum of AI would be, of AI squared would be n, right? AI is 0 except in one location, A is 0 except in one location is square root of n, so the maximum squared coordinate is n. It's very, very coherent, so the coherence is n, it's maximum. It's a very coherent sensing vector, and we could see that if we were to use this sampling scheme to actually sense a one sparse signal, a signal with only one spike, I would need lots of measurements. And how many would I need? Yeah, at least n. But if I really take these things at random, n log n, that's good. That's a coupon collector problem. Yeah, n log n. Yeah, so if I were to pick coordinates at random, it's like, I'm sure you've seen these things in elementary probability. When you pick coupons at random, how many draws do you need to be able to have a complete collection? I think 2n log n. Okay, so you would need n log n samples. Okay, so now we're going to look at more interesting sensing mechanisms, which are incoherent sensing processes. The first, the easiest one, according to my definition, would be a binary sensing, where now I'm going to pick a random waveform such that all of its components take two values only, plus or minus 1 with probability 1/2. Okay, so that would be something that looks like what you see at the top. So I have a random sequence of a vector. A sensing vector is simply a random sequence of plus and minus 1s. We're going to call this a binary ensemble. Obviously, A star is the identity because the coordinates are actually independent. So A of AI AJ is 0 when I is not J by independence. And when I equals J, that's just 1. So obviously, this is an isotropic sensing mechanism. And the good thing about this is that the maximum entry of A squared is 1. And so we see that we achieve the minimum coherence. Right, so this is an example of an incoherent sensing process that achieves the minimum value of the coherence. Okay, that's one example, and that's our first example. It's obviously a very easy example. Another example would be to take white noise. So it's essentially the same thing, except that instead of sampling, of having entries which are plus or minus 1, so it's probably 1/2, I have Gaussian entries, which mean that in vector forms, the sensing vector A is normally distributed with mean 0 and covariance the identity. And in this case, by independence as well as before, we have that the expected value of A star is the identity because the coordinates are independent just as before. The coherence now is a bit larger because I think everybody knows that the maximum of absolute value of white noise of n realizations of Gaussian variables is about square root 2 log n, which means that the maximum value of AI squared will be of size roughly 2 log n. It's still very, very low compared to coherent measurement. Okay. Now these are matrices that are called, is the sensing matrix that result from the first two examples of measurements would be matrices with IID entries. Each row is independent, and then each element in a row is independent, so you have independence everywhere. And now we're going to look at more structured measurements, which is very important to keep in mind because in applications we only use structured measurements. We don't really use IID matrices for reasons that I will explain toward the end of the week. Essentially for computational and storage region. If you have a system and you want to apply compressed sensing, and let's say you want to sense images, and let's say you want to sense things with 20 million pixels, and you want to make 500 or 1 million measurements, we're not going to store IID matrices with 1 million rows and 20 million columns. It's out of the question. Instead, what we would be happy with is something like this, where here is a very different kind of sensing mechanism, where now I'm going to select a number k between 0 and n minus 1 at random, and then my sensing vector will just be a sinusoids at that frequency. Okay, so now I have a bag of sinusoids. Okay, and then each time I want to make a measurement, I pick a frequency at random, I measure that Fourier coefficient. Right. Another way of looking at this is we select IID rows from the discrete Fourier transform. Okay, so each time I take a row of the Fourier transform, and that's my first of the discrete Fourier transform in that first row. You want another measurement, I pick another row from the Fourier transform, that's my second row. Okay, this process is also isotropic and incoherent. In fact, it achieves minimum coherence as well. And so if I look at the expected value of A star at the coordinate t prime, then, well, it's given by this formula. It's 1 over n, which is the probability of picking frequency k times the sum over all possible choice, sum of k exponential I2 pi k t minus t prime. That's a formula for the t prime component of A star over n. So that's just the formula. It just plugs the numbers. Okay, and we all know that it's a Dirac. So if it's 1 if t equals t prime and it's 0 otherwise, and so we've got that the isotropy is fine. It's checked. The coherence is great here because the coherence would be the maximum value, absolute value of a sinusoid, but it's 1. So we have isotropy and minimal coherence as well. Okay, so in that sense, the binary and the Fourier measurements are both isotropic. They're very different because, as you can see, they have a very different structure, but they are both maximally incoherent and isotropic. Okay, but they're very different beasts. Fourier, extremely hard to say something about it. Matrices with IID entries, easy, much easier. Now, of course, you don't have to limit yourself to the discrete Fourier transform. You can have a unitary matrix somewhere that you like, such that U star U is equal to the identity. You're going to select rows. Each time you want to make a measurement, you pick a row of this unitary matrix at random, measure, pick another row at random, measure, And of course, that will be isotropic. And the coherence is not going to be hard to see that it's going to be bounded by the maximum entry that you see in your unitary matrix. Right, so there are many examples of problems of sensing mechanism that would obey these two properties we're seeing. I'm going to show you others. So for example, why in the previous example I was picking rows from the discrete Fourier transform, why do I have to restrict myself to frequencies that are exactly of the form 2 pi k over n? Why do I just don't take any arbitrary frequency? So I could observe a random frequency, so I could pick omega uniformly at random in 0, 1 now. Right, so it doesn't have to be on the integer lattice. I would set the sensing waveform to be exponential I 2 pi omega t, and that would be perfectly fine. It would be the expected value of A star. Now it was a sum, now it becomes an integral, but it's still the identity, and it's still maximally incoherent. Right, so I can select frequencies from the continuum if I want, and I can do lots of things. For example, random convolutions would fit this model as well. So I would have a convolution matrix, which happens to be diagonal in the Fourier domain. So convolutions are, of course, diagonalized by the Fourier transform. And if I were to make sure that the eigenvalues were of the same size, then I could just sample output of a convolution product at random locations, and that would fit the model perfectly fine as well. So I can do lots of things. I can create random sensing vectors that are highly structured. I can do random convolution. I can do Fourier. I can do lots of things. Okay, so this is a framework that accommodates lots of sensing mechanisms. Not all of them maybe, but lots of them. And if we were to able to relax the assumption on the coherence, saying that the covariance just needs to be bounded below and above, then I think we would cover pretty much all that I'm familiar with. Okay, so now that we have this very simple sensing mechanism, what can we say? Okay, so now we're going to sample sparse signals. So we're going to pick each row from this population F. We're going to assemble these equations. And so we're going to try to solve it. And of course, how do we solve it by L1? This is what we saw yesterday. Okay, and so the first theorem emphasizes the role played. The first part of our first theorem. This is our new result. The first part of the theorem says that the coherence really plays a fundamental role. That even if you did not want to limit yourselves to L1, if you could solve an L0 problem, or if you could solve anything you want, then I claim that no method whatsoever can recover X with high probability unless the number of degrees of measurement is bigger than mu times S times log n. So the coherence really puts a lower bound on the number of measurements you need for any method whatsoever to succeed. And so the bound has a simple expression, is that we have a numerical constant here, but really the important thing is that the lowest sampling rate you could ever achieve is the coherence times the sparsity times log n. Okay, so for example, if S were 1, as we've seen before, then what it says is that if you use, and the coherence was n as the very coherent measurement we've seen, then we recover the result I was quizzing you about, which would be the number of measurements we need is n log n, which is this coupon collection effect. All right. Okay, so the number of measurements we need, of course, this is provided that this quantity is less than n log n, because if you make n log n measurement, you see everything, and so you need n log n. So you need coherence times S times log n for any method to succeed, even if you could solve combinatorially hard problem. Okay? But if you use L1, then as soon as you're about this level, so in this lecture, every time you see here is like I'm not specifying a constant. Okay, so wiggle means there's an O1 here. Okay, so, but with very high probability, if the number of samples is exactly on the order of mu S log n, then we know that L1 will succeed with very high probability. High probability, of course, over the sampling scheme. So with very high probability, we know that with fewer than mu S log n measurements, you can't do anything, and with mu S log n measurements, actually, the L1 solution will be exact. Okay, so that's good because what it says is that if I have a sensing mechanism which has coherence, low coherence, then I can sense very efficiently, of course. Right? So for example, if I were to use Fourier or the binary ensemble, all these measurements that we've seen with coherence equal to 1, what the result says is I just need to pulse the signal s log n times, and that will discover the location where it's not 0 and the magnitude. All right, any questions about this? Yeah.
So that's for one fixed x?
Yes, it's for fixed x.
So do you have results on point where you looked at a lot of x's at the same
Yes, so that's this afternoon. That's a deterministic theory. So it's a very good point. I'm sorry I did not emphasize. I said x at the beginning is s sparse, it's fixed. So it's in this kind of slide, it's important, the order of quantifier is important. Fix x, randomly generate measurements, can you recover that x? Okay? And what this says is yes. In fact, you can fix x any way you want, as long as I make s log n measurements, I will recover that x. What I cannot say here, which is, I think, where you're getting to, is that I cannot say that my measurements will recover all sparse signals. This I can't say, but I can recover yours, which is what I care about. REA goes in a scan. The scan takes Fourier measurements because it takes an MR, and I can recover REA. And that's all I care about. Okay?
Okay.
All right. Okay, so that's very important in the theory, that this says that we assume that the signal can be set any way you like, but it's fixed from now on. And then we make random decisions as what to measure, and then I can guarantee that the signal will be recovered exactly. What I cannot say again, and I'll emphasize this, is that now suppose you've seen my A and you want to pick a sparse signal which is really bad for me, then I cannot guarantee that I can recover all A's, all sparse signals. But I can recover yours, which I think is what we care about.
Yes. If x is not exactly s sparse,
Mm-hmm.
but
We're going to get there.
okay, good.
Sorry, are you saying that basically the constant b depends on x?
The constant?
The proportionality constant between n?
No. No, it's independent of x. No. Excuse me?
Uniform in x.
Yes. This is like, for Fourier, I think with Terence, we could, and Justin Romberg, I think we could prove that it was 15 or something like that. Okay. Any other questions? These are very important.
So is there a reason that, so mu of f for you is deterministic, but from the definition it could be random as well in principle? Mu of f, the coherence constant.
It's a deterministic quantity, yes.
It could be random from the definition in principle.
Well, yes, it could be random, but it's a likely upper bound on the maximum entry of the sensing vector. That's what it is. Okay. All right, so this really works in, well, that's... Okay, so that's an image that we've seen yesterday. This image is sparse in the wavelet domain because I killed all the little coefficients. And so it's 25,000 sparse, and I'm going to make 95,000 measurements of this image, incoherent measurements. I think these are, I forgot what they are. They're some kind of scrambled Fourier measurements. And then I recover the signal by L1, and it's exact. It's numerically exact. Why? Because we know that we can recover S sparse vectors exactly by L1 minimization from incoherent measurement, and that's what this shows numerically. Okay. All right, so now I'm going to go to your question. It says, well, in general, things are not sparse, and that's very important, because in general, I have a signal which is arbitrary, that it may not be sparse at all. And what I would want is I want to go back to the lecture we had yesterday where I want to compare how well I'm doing compared to someone who would be able to see the largest components of X. Okay, so this, from now on, XS is going to be a very important guy. It's essentially the best approximation of the signal X using only S non-zero coefficients. So XS is a minimum distance between X and Z, where Z cannot have more than S non-zero coefficients. So of course, what is XS is like you look at the signal X, you pick the S largest coefficients, you zero out everything, that's XS. Okay, so I want to compare how well I do with someone who has seen the signal ahead of time, knows exactly what to measure. And me, of course, I don't know where's the big coefficient. I have to discover it. And so the result goes something like this. I pick a fixed x. I'm going to define m as before. M is the coherence times s log n. And what we've got is that for example, the distance between x hat and x in the n1 sense is comparable to the distance between x and its best approximation. So you would not be, so if I knew ahead of time which coefficients are large, and I would just go out and measure them directly, what I can guarantee is I come within a small factor of this thing if I take roughly mu times s log n measurements. There are error bounds in two norms. In N1 sense, we can get this. In L2 norm, we can get the same constant, but with an L1 term divided by square root of s. Now, what is this factor alpha? Well, alpha is something like log m, log of the number of measurements. Sometimes this factor disappears, but just to be on the safe side, I'm going to put it in. Okay, so I can get within a logarithmic factor of what I would get if I could see the largest, if I knew exactly which are the largest coefficients, what are the small ones, and I would just measure the large one. Does this answer your question? Okay, all right. So this is what I would say is kind of, the best approximation I can guarantee with S non-zero coefficient is this. And what I can get is what I can get within a small factor of this. By sensing the signal very few times, is essentially S log n times. Okay, so of course, if the signal is sparse, then that's 0. So we recover what we had before. Then, of course, this is 0. This is 0 as well. So, of course, this theorem is more general than the previous one. It would say that if you had sparsity, then the error would be 0 because the right-hand side it would be 0. And otherwise, what you're getting is essentially the accuracy you would get by essentially being able to measure the important coefficients and not what is not that important. By measuring what Brian Hayes called the best bits.
It wouldn't change. So assuming that X is not necessarily sparse or not completely sparse, wouldn't change a priori the number of measurements that you need to recover it by L1.
No, I think this is always the same discussion we have. No, of course it changes. I mean, it depends what is your goal. So really here I want to make this connection with data compression. The number of measurements is really, in this theory, equivalent to the number of bits you have at your disposal to compress a data set. For some data set, that might be enough to achieve a low distortion. For others, it may not be. All right? So what you have to tell me is, are you happy with this or this? If you're happy, if this is small, if it's eye-pleasing in the sense that it's small enough so that your eye likes it, then I say, yeah, use that S. So do S times that log n. If you're not happy with this because the signal is very complex, then you can't. You have to sample more. And so you have to sample more. Pick an S so that the distortion makes you happy. Oversample it by log n times, and that's the number of samples that you need to get. Yes?
Do you have a sort of converse result like you had for the exact sparse that says no method can do better? No other method can do better?
Yeah, I mean, the thing is, what you can show is that, so the converse result is something like this, which is that I can give you a sparse vector. I can give you two sparse vectors that have disjoint support, roughly the same energy, and give me the same data. So if that's the situation, then I'm going to make a big error. So there's really a converse theorem.
And that carries through to the approximate case as well.
Right, but that, yes, because what it says, we would say that somehow this is large because the signal is not well approximated by an S. Yeah. Okay, and so I want to kind of go back to Mike's point yesterday, which I think is very well taken, which is that in many cases we have physics, we have computational constraints, we have storage constraints, And for all of these reasons, the sensing matrices that we can use in real life may not be IID Gaussian. And so it's important to understand what sensing matrices we can use that kind of obey the physical constraint that Mike was talking about yesterday, that are easy to multiply, for which that are easy to store. And so this is what this is trying to get at. Okay, so there's a special case of this result, which is an earlier result of Justine, Terence, and myself, which to some extent was at the beginning of this compressed sensing business. So it was saying that if we had S-sparse vectors, and if we were to look at S log on the order of S log n Fourier coefficients, then that would be enough for perfect recovery by L1. And so what you're seeing in this result is an extension of this result that says that, you know, what is true for Fourier is true for lots of measurement ensembles as long as I have this low coherence parameter. But that's an important precursor of this result, which was just in the special case where the sampling mechanism is revealing Fourier coefficients of a signal and these Fourier coefficients at randomly sample. Okay. So in practice, of course, it works well. Like, here's a signal that has 15 non-zero terms. I'm going to observe only 30 Fourier coefficients, complex, so it's really like 60 numbers, if you will. And when I solve L1, it's perfect. And if I solve L2, that's a disaster. Okay, because what is L2 doing in this case? Because we have a perfect isometry between time and frequency, the Fourier coefficients that you don't get to see, you set to 0, because that's what minimizes the L2 norm. And so you reconstruct a sparse trigonometric polynomial that has nothing to do with a sparse spike train, of course. And what you're seeing here is a sparse trigonometric polynomial. Okay, so we can do, well, that's not going to be very useful. Of course, the image, of course, this theory has lots of extension, which we cannot discuss really, but the signal may not be sparse, like, you know, it could be, its gradient might be sparse, which is the case for these Logan-Shep phantoms that unfortunately we can't see. And in this case, it would minimize the L1 norm of its gradient since the gradient is sparse. And if you were to use filter back projection, which is what kind of algorithm that Mike discussed yesterday, that would not go very well. But if you minimize the total variation norm, which is the L1 norm of the gradient, then of course you would have perfect recovery for exactly the same reason. All right. Okay, so let me try to explain why is it that we need mu S log n samples, and why is it that we cannot do with less. Okay, so I'm going to do it in the case where mu equals 1, and then there's a very easy generalization to the general case. That basically you just repeat this construction in a slightly different way by you create a block diagonal population, if you will. But I think if we understand mu equals 1, why we need S log n samples, and we cannot do with fewer samples, then I think that we'll get everything. So I'm going to assume that the signal size is a product of two integers, S and tau. S is our sparsity, and tau is, of course, n over S by definition. And I'm going to take a spike train. So I'm going to take for x what as a kid I learned was a Dirac comb, and it's a signal that is 0 in lots of places, except every tau it's 1. Okay, so it's a signal with lots of zeros which are here, and from time to time it takes the value 1 every tau samples. Okay, so it's a Dirac comb. It's also called the Pickett-Feld signal. And its mathematical definition is what you see at the top, right? So I put a 1 every tau. Okay, so that's what we see at the top. Okay, now I'm going to sense this. So now I have my sparse signal, and I want to sense it. And so I'm going to use, let's say, the Fourier ensemble to sense it, which has very low coherence, mu equals 1. And so I want to show that if you sense it, if you measure Fourier coefficients, then I'm going to need to see at least S log n Fourier coefficients of this guy. Otherwise, trouble arises. Okay, so what I'm going to claim now is that the Fourier transform, the discrete Fourier transform of this is kind of the discrete version of the Poisson summation formula. is another Dirac comb, except that the spacing between the spikes now is S. Okay, and if you want this, the spacing, it obeys this uncertainty relation, that S tau. Okay, and so now I claim that the Fourier transform of a signal like this is another Dirac comb in the Fourier domain, but now there is the spikes are S apart. So I have here I have tau, I have S spikes. Here I have tau spikes. Okay. All right. And so there's a little formula. There's a little proof that proves this thing, but I think I'm going to skip this. It's just on the board. So it's a very trivial calculation. So that's what we have. Now suppose that I take on the order S samples. Then each time I'm sampling, I'm going to probably miss the spikes. In fact, with probability 1 minus 1 over S, I'm going to get to C0. Right? Because with probability, or with probability 1 minus 1 over tau, what is it? Somebody can help me. Yeah, 1 minus tau over n, I'm going to see 0, right? Okay, so with probability 1 minus tau over n, so when I take Fourier samples, many times I'm going to miss these spikes. And so with probability 1 minus tau over n, a Fourier sample will give me 0. And now I'm going to do this independently. And so I'm going to calculate that with very large probability, I could see zeros if I don't take enough samples, because if I take too few, they will all avoid these spikes. I will see 0, and I will never be able to tell what my signal is. So a mathematical argument will look like this. It says, okay, we have our Dirac comb. If I observe a frequency at random, x hat of k will be 0 with probability 1 minus tau over n. And so the probability, because I have independent sampling, the probability that all the measurements vanish will be just this probability raised at the power m, which is 1 minus 1 over s at the power m. Okay, and we're going to see that if m is too small, this is kind of large. If m is small, then with large probability, or with some probability, all the measurements will vanish, and so there's no way I can say that you did not give, I'm not sensing the 0 signal. Okay? And so, for example, any method would fail with probability at least 1 over n. If 1 minus 1 over s at the power m is greater than 1 over n, another way to say this is if m log 1 minus 1 over s is bigger than log 1 over n. And so we see that any method would fail if m is less than s log n. So if I want a probability of success which is decent, then I need to sample s log n times. I cannot do with fewer. Otherwise, you risk. Otherwise, there is Heisenberg that says that I can be sparse in the time domain, I can be sparse in the Fourier domain, and you could just get to see zeros many times, and there's nothing you could do. Okay, so that's kind of what explains why we need S log n samples, and we cannot do with fewers. And of course, this extends to arbitrary coherence. What you do is you're blocking the Fourier transform to have a block diagonal Fourier matrix, and that would be the way you prove that mu times S log n is the absolute lower bound in general. Okay, all right. So now we've seen that we need at least mu S log n samples, and what we try to explain now is why is it that that number is actually sufficient for L1 minimization. So we're going to spend the last 20 minutes discussing L1 solutions now, and first I'm going to show you what L1 works, which I'm sure people have seen before. Okay, so I have a sparse vector x, and I can only draw in the plane, so this sparse vector x is going to be 0 on this line and not 0 on the vertical line, so it's a point on the coordinate axis like this. Okay. Now, unfortunately, I'm very poor, so I can only afford one measurement. So at the end of the day, I have this equation that says, well, the sparse vector x is somewhere on this line, but I don't know where. Well, if you're classical, you could say, well, I'm going to try to find a minimum energy solution, and I'm going to try to find a point x with minimum energy on that line. And And so we would draw this ball, see when it's tangent, and we get a reconstruction, which is of course a orthogonal projection of the zero vector onto this plane. In 2D, it doesn't look too bad. In high dimensions, it looks like this. Okay, so that's not what we want. But now we said, but we're going to minimize the L1 norm instead. So what is the L1 ball? The L1 ball looks like this. Okay, so that's the L1 ball. Okay. And now we say, what is this point on this line, which has minimum L1 norm? Well, that's the point that is tangent to the L1 ball, and that's the chi you see here, and the recovery is exact. Okay, so I have a sparse X. I have made only one measurement, and I have exact recovery by L1 minimization. Okay, but of course we have to be careful because we could have this also. Like if I had taken a different measurement, I would have a different equation. I would find the L1 solution. I would get another sparse solution, by the way, but not the correct one. Okay. And so what the theorem says is it says that if you sample S log n times, you're never in this situation. You're always in this situation, right? Somehow the null space of your sensing matrix, which is of course this red line that you see here, is always tangent to the L1 ball at the right point. So what the theorem says is that with S log n measurements, you always like this and never like this. Okay. Now, suppose we were taking one Gaussian measurement, so I can only afford one Gaussian measurement. What would be the probability of recovery of a one sparse vector with one in 2D with one Gaussian measurement? I would get the right hand side, what fraction of the time? The right answer, what fraction of the time? 50%. 50% of the time, one Gaussian measurement, because of course this line would have a random orientation, and if this orientation is in the minus 45 plus 45 degree line, I would get the right point. If it's in the other cone, so then I would get the wrong point. So with one Gaussian measurement, I would actually recover one sparse vector 50% of the time. But with S log n Gaussian measurements, all the time. Okay, so let's look at optimality conditions. So how do we prove these? Some of the theorems. Of course, I can't prove these theorems because some of them are involved. But I will try to give you a simple proof of an easy result. Okay, so how do we show that the L1 so how do we characterize the L1 solution? Well, a point X will be solution to the mean L1 problem subject to AX equals B if, of course, the null space of A, which you see here, is tangent to the L1 ball. So that's really the picture that everybody in the business has in mind, which is that we're going to have exact recovery. A solution X is going to be solution if the null space of A is tangent to the L1 ball at X. Okay, and that's the picture that everybody in the business has in mind. Okay, so one way to characterize this, so it's like you can go, so we've seen that an L1 problem is a linear program, so you could go through the linear programming optimality condition or KKT condition, and I'm not going to really do this. I'm going to say that X is going to be an optimal solution for your optimization problem if you can find a vector V which is in the row space of A, that is orthogonal to the null space of A. The row space of A is orthogonal complement to the null space. If I can find a vector V which is orthogonal to the null space of A, which is equal to the sign of X when X is not 0, and so T is going to be the support set of X. So from now on, T is the support of X. And so X is going to be an optimal solution for our optimization problem if I can find a V which is orthogonal to the null space that matches the sign when xi is not 0 and is less than 1 otherwise. If I can find such a V, which is essentially the dual optimal dual variable in the KKT condition. If I can find such a V, then this V certifies that X is solution. And that's why such a V, we're going to call it a dual certificate. If there is such a V, then it certifies that X is a unique solution, that X is solution. If in addition, I can make sure that outside of the support, V is strictly less than 1, and that the matrix A restricted to the support set. So AT now, it's very important what AT is. AT is the columns of A restricted to the support of X. It's a submatrix of A restricted to the column of X. If I can, in addition, make sure that VI is less than 1 outside the support, and AT has full column rank, then that will be the unique solution. There's only one point of contact, and that's this guy. Okay, and that's what you see here. You say, can I find a vector in the orthogonal to the null space that matches the sign and is less than 1? So can I find a vector which is orthogonal to the, in this, can I find a vector which would be of the form epsilon 1, which is in the orthogonal to the null space of A, where the absolute value of epsilon is 1, is less than 1? Yes, of course, because I've drawn 1. So that would say that this X is solution and it's a unique solution. And so some of the proofs in comparison sensing say, I have a candidate solution. I want to show that the recovery is exact. Let me just find a dual certificate that will certify that this solution is exact. Okay, so we call this V or this lambda a dual certificate. Now I'm going to try to show you that this is actually true, that if VI is strictly less than 1 and AT has full column rank, then X is a unique solution. And that's not difficult. So from now on, XT will be the restriction of X to indices in T, and AT would be the submatrix that we have already introduced. And if the support of X is included in T, by definition, we have AX equals ATXT. Okay, so let's go through the proof. I want to show that if I'm at X and I'm trying to move away from X, I'm going to increase the L1 norm. So that, unless H is 0, the N1 norm will increase. So how do we do this? Well, we're going to split so we look at the L1 norm of X plus H, and we say the sum of absolute values of Xi plus HI, and Xi is 0 outside of T, so it's the sum of absolute value of Xi plus HI plus HI over T complement. And now I'm going to use this profound inequality that says that Xi plus HI is greater or equal to Xi plus the sine of Xi times HI. Okay. That's what I'm using. All right. And so I have this inequality. But I know that the sine of Xi is Vi. So I'm going to replace this with Vi. So it's the norm of L1 plus the sum of VI HI, since VI is equal to the sine on the support, plus the sine of HI T complement. And now I'm going to add and subtract the sum of VI HI on T complement. So I'm going to add the sum of VI HI on T complement and subtract it. And so what I'm going to get is, by adding the sum of VI HI on T complement, I'm going to get the inner product between V and H. And then I'm going to subtract it, and so I'm going to subtract 1 minus Vi, so it's certainly less than if I subtract the, greater than if I subtract the absolute value. But now, of course, V dot H is 0. Like, that's the whole point. V dot H is 0 because V is in the row space of A, so V is of the form A star lambda, and so therefore V dot H is lambda dot AH, but AH must be 0 since A of X plus H needs to be feasible, and X was feasible, so AH is 0, and so this is 0. Okay, so AH is 0, and therefore V dot H is 0, right? Because H is in the null space of A, and V is orthogonal to the null space of A. Okay, that's what we had before, right? V is in the orthogonal to the null space of A, and H is in the null space of A, so it has to be feasible. A of x plus h has to be equal to ax, so ah is 0. Okay, so that goes away, and now I have this. But now, if Vi is strictly less than 1 on T complement, this is going to be strictly positive unless all of the HIs are 0. And so what we've established is that the objective will increase, strictly increase, unless H restricted to T complement is 0. Well, so the only way I can keep a constant L1 norm is by forcing H outside of the support to be 0, but then x plus h is feasible, which means that h will be 0 since I would have to have AT equals 0, but AT has full column rank, so how can it be? The only possibility is HT is 0. And so what we have proved is we have proved the result, which is a very simple result, which said that if I can find a dual certificate which is orthogonal to the null space is strictly less than 1 and AT has full column rank, then of course the solution is unique. And that's what we're going to use to actually show that L1 solutions produce the right answer, is by showing that I can actually construct such a dual certificate. Okay, so we're going to prove a first easy result, and we're going to follow a strategy, which is a strategy we took with Justine and Terence, where we're going to explicitly construct a dual certificate. So I want to show that I can find such a V. I have a candidate solution, which is, of course, the truth, and I want to show that the truth is indeed the solution to my L1 problem. And so I'm going to guess the form of a dual certificate. And the form of the dual certificate is at the top. I'm going to take the sign vector, the sign of x. So the sign of xt is, of course, plus or minus 1. And I'm going to hit it with this matrix. Well, V is, of course, of the form A star lambda, so it's orthogonal to the null space. That's what we want. By construction, it is. When I look at the restriction of V to the set T, well, it's going to be this. So this is the identity. This is a sign. So it gives me the sign. So I need three properties. Orthogonal to the null space, checked. Reproduces the sign, checked. Now I have to show that on T complement it's less than 1. That's what I need to do. So if we could show that if Vi was less than 1 for I in T complement, we'd be done. And of course, this is where all the work here is here. And the interpretation of why is it that we constructed this dual certificate is that experts will recognize that this is somehow a least square solution of some problem. And what problem are we solving here? Our construction of a dual certificate is try to find a V which is orthogonal to the null space, matches the sign, and is minimum in an L2 sense. Okay, and if you solve this least squares program, you'll find that V is given by this equation. And for us, why did we do this? Because we have a formula, so we can try to check that Vi is less than 1. And second, this kind of makes sense because this is going to try to minimize the energy of V. And by minimizing the energy of V, I'm hoping that outside of the support, I will be less than 1. Think about if you were to do Fourier, what you would need to do, if you wanted to prove a Fourier result, you need to prove something that looks a bit kind of difficult. Well, if we had Fourier measurements, what you want to do really is you want to find a sparse trigonometric polynomial that only uses the frequencies you got to see, and that would interpolate the sign vector. Right? So if we were to do Fourier, what I would need to find is a trigonometric polynomial that only uses the frequencies I get to see. That's what it means to be in the row space of A. That interpolates the sign sequence and then is strictly less than 1 everywhere else. And the question is, can I find such a thing? If I can, then I prove that the recovery is exact. So to do it for Fourier is not trivial at all. And so what I'm going to do it is I'm going to do it in a trivial case. And I'm going to do it for the Gaussian case. And in fact, what's nice about this approach is that you can get really very tight constants. So you can see what the constants become. So let me move away from Fourier and say, how many Gaussian measurements do I need to recover an S-sparse signal from y equals ax, where now the entries of A are IID Gaussian. And what we'll see is, in an asymptotic sense, just because I don't want to keep track of too many constants, we need 2s log n. So the constant is known. Okay. And how are we going to do this? We're just going to use our construction. I'm going to say V equals this, and all we need to show is that we need to show that, well, first of all, I need to be able to do this. So I need that A star T or AT has full column rank so that this matrix is invertible. And I need to show that VI is less than 1 for each I in T complex. So let's do this. OK, so what we're going to do is we're going to say, all right, what is this vector in the first place? So I have my Gaussian random matrix. And I want to show that VI is less than 1. And what is VI? Well, VI, by definition, is going to be the inner product between, so I'm going to split A star into, I'm going to write V equals A star W. And W is this. And VI is then simply the inner product between W and a column of A. So I have a column of A, which is, so I'm going to say that we have the support T here. I'm going to take a column of A outside of the support. This is going to define a vector W. And so I'm going to look at the size of the inner product between W and AI. OK. Now, and that's the beautiful things about IID matrices, is that W and AI are independent. Because W only cares about what's happening here. AI is here. This is independent, so they are independent. For Fourier, that is absolutely not the case. Right? The columns in the Fourier, in the subsample Fourier matrix have no independence whatsoever. And that's what makes the analysis, the compressed sensing analysis of structured measurement extremely difficult, that you don't have this independence. But for Gaussian, we do, and that makes our life simple. All right. So if I condition on W, if I assume that W is fixed, then because AI is a Gaussian random vector, then VI would be Gaussian with mean 0 and variance W squared over M. Right? So conditional on W, I know the distribution of VI. It's an inner product with a Gaussian vector and a fixed vector. It has to be Gaussian. Right? It's Gaussian with mean 0 with known variance. So I can say that the probability that VI is greater than 1 given W is less than 2 to the minus 1 over the variance, 2 times the variance, which is what you have here. Okay, that's really, really elementary. Okay, so so if W did not have a big norm, then we could see that if W had a norm much smaller than M, then we could see that we're done. So now, does W have a norm much smaller than M? And yeah. What do we know from standard matrix theory, which we'll review a bit this afternoon? We know from standard, in fact, I will justify this in the afternoon, that we know that if you give me a Gaussian random matrix, which is like this, I can lower bound the minimum singular value of such a matrix. And in fact, I know that the minimum singular value of a Gaussian random matrix is less than 1 minus, the probability that it's less than 1 minus square root of S over M. So I have S columns and M rows. Essentially, the minimum singular values is of size roughly 1 minus square root of S over M. And the probability that it's a bit smaller than this is exponentially small. Okay, that's standard Gaussian matrix theory. All right, but that's all good because it says that I can bound below the size of the minimum singular value of AT, and therefore, no matter what the sign pattern is, I know that the norm of W would be less than this matrix norm times the norm of the sign, but the norm of the sign is, of course, square root of S. Well, that's what it is. And the norm of this matrix is, of course, 1 over the minimum singular value. But I have a bound. I know that the minimum singular value, it cannot be lower than this. So I have a bound, so I just put it in. Okay, and so I've got this. So I know that the size, the norm of W is going to be less than this with enormously high probability. In fact, it's going to be bigger than this with exponentially small probability. Okay, so now I have two things. I have that given W has this, and I know that W cannot be too large. And then I just put them together. And how do I do this? I say that the probability that the maximum exceed 1 is the probability that the maximum is less than the probability that the maximum exceed 1 given that W is less than our bound, plus the probability that W is bigger than our bound. But then I'm going to use a trivial union bound. The maximum is less than the sum of the individual probabilities, so it's less than 2 times n times exponential minus m2b squared, which is just by plugging the bound I have for w in here, plus the probability that w is not of the form I want, but that we've seen is exponentially small. And now you just replace b by the expression you see, and what this analysis gives you, it gives you that, well, if you give 2 plus epsilon s log n measurement, you'll see that you get exact recovery with overwhelming probability as n goes to infinity. So that's an asymptotic result. And if you want a finite result, then you would see that with 3 s log n measurement, that's enough as long as n is greater than, I don't know, 500 or something like that. Okay, all right. So this is kind of how it works. So once we understand how we can certify that L1 solutions are actually exact, what we do is we need to find a dual certificate. We can use this construction to find it. And if we are lucky enough to have a matrix which has IID entries, then we can use the independence between what's happening here and what's happening here to actually bound the value of the dual certificate outside of the support and get what we want. In fact, there's really nothing about Gaussian matrices that I use. Here, if you had matrices which were, let's say, plus binary, then you could use Hoeffding here. And we also know large deviations for the minimum singular value of a binary matrix, so that would carry without any modification whatsoever. Okay, so it works as is with matrices with sub-Gaussian tails, and so on. Okay, so the summary of this lecture is we see that we can actually acquire signal efficiently by random sensing. The acquisition is non-adaptive, and the reconstruction invokes linear programming. We need incoherence, and it's surprisingly effective. That is, L1 seems to work almost as soon as any methods work. Thank you.
What are the penalties of using the binary matrix?
The penalties in
Is there any disadvantage to it?
computationally, yes, because you need to store it, and so
You can generate it from pseudo-random binary.
sure, of course you can generate it, but each time you want to calculate AX, you're going to have to generate the vector. That's very expensive. So theoretically, it's great. The binary matrix is great. The Gaussian matrix are great theoretically. But first of all, as Mike said yesterday, they don't really arise in physical experiments, and so we have to deal with this. And two, I would say that from a practical point of view, one we're going to talk about, so it's very important for us to be able to, if we want to deploy this in application, it's very important for us to solve this L1 problem effectively. Now, at the bottom, at the core, what we'll discuss in lecture 7 is at the core of all these minimization algorithm is I need to be able to compute AX and A transpose Y rapidly, because it's going to be a lot of sequential matrix vector multiply. So for a large binary matrix, that's going to be very expensive. It's going to be order mn each time. And to me, that's a dramatic limitation. I need to store it, and if I don't want to store it, I need to generate it each time. I need to take it out of memory, load it in memory, calculate it, then dump it, and it's impossible. And that's what I like so much about the Fourier transform. I don't need to store it, and I can apply it in n log n times.
What about the Walsh-Hadamard matrix?
That's good. That we like everything that is structured. We like every compressed sensing matrix that I don't need to store, that come with a fast algorithm, that has this incoherence property. Of course, I like. Yes.
When you're considering the Gaussian or binary, you've got no structure at all on 1 up to n. But when you're doing Fourier transforms, you're ordering them.
Of course.
Is that significant? The difference?
No, the theory is the same for both. I mean, in terms of what's possible, it's the same for both. The Fourier transform is highly structured, and but the theory applies to both unstructured and the structured. And most of the compressed sensing theory deals with IID matrices, and I think that's great, but that's also a bit of a limitation because, as I said, in applications, I think they're hard to use. But the structured matrix like this are very, very handy. Now, what's important to understand mathematically is that the proof you've just seen for Gaussian matrices, which is essentially half a page, if I were to write it down, for matrix for Fourier becomes, it's extremely complicated, unfortunately. And that's where it involves a lot of combinatorics to actually try to find, because, try to show that this dual certificate is indeed, first of all, how do you bound the singular values of a sub-Fourier matrix? How do I show that if I have a Fourier matrix and I restrict its I have sampled some frequencies, I take a fairly large support, how do I show that this guy is well conditioned? It's not obvious already. But structured measurements are very important for us. Very important. Now, of course, I could cheat, because what's good, maybe I can extrapolate the question a bit. Now, you give me a Fourier matrix, but for some reason you don't like it because you don't like the ordering. There's nothing that prevents you of creating a Fourier compressed sensing matrix that does this. Take the Fourier transform and permute its columns in a random fashion. Then you destroy the temporal structure. The incoherence stays the same, of course, because incoherence is invariant by permutation. The isotropy doesn't change. And so you have a matrix which, from my point of view, is exactly the same. But maybe for you it's better because now you destroy the temporal structure. So you can actually take structural matrices, apply random permutations, and create matrices that you might like.
Okay, well, maybe we pause for now, and we will continue at 2 p.m. With the third lecture, and let us thank Emmanuel.